Hello and welcome back to the final part 5 of the Tortoise-TTS Fully Explained series. In this video we will take the MEL spectrograms that we generated in the last video and we'll transform them to waveform audio, meaning we transform it to a speech file that we then finally can listen to, and this brings us to the end of this series. And as always, let's just jump right into it. Yes, and as almost always, we start with temporarily loading the vocoder to the VRAM, and then we initialize an array called generated speech, in which we then will collect the transformed speech files using the vocoder. And as you hopefully remember from the last part, we have the array generated MEL spectrograms, which we defined here, where we collected all the generated MEL spectrograms using the diffusion model. And then before we can pass those MEL spectrograms to the vocoder, we need one pre-processing step. So this time it's pretty smooth and easy to pre-process. So we invoke the denormalized tachytron MEL method, and the name already says what this kind of does is it denormalizes the MEL spectrogram that we have generated in the last video. And if you want, you can also go back and see the output values that we had. Those were normalized between -1 and +1. And in the Tortoise library, we can also see the denormalized tachytron MEL function or method. And here we can see that the method takes a normalized MEL spectrogram as an input and then transforms it or denormalizes it to the range of -11.5 and 2.3. So what this basically does is, before we have values in the range from -1 to +1, and the spectrogram that we return have values in the range from -11.5 to +2.3. So that basically a value that was before -1 is then -11.5 around, and a value that before was 1 is then around 2.3. So we denormalize the MEL spectrogram to the range of values the vocoder was trained on. Yes, and then we can pass the denormalized MEL spectrogram to the vocoder and invoke or call the inference method, and as a result we get our waveform audio, and this we can then append to our generated speech array. In step 13 we can play it. Before we go there, I quickly want to explain a little bit more about the vocoder, because it's very well abstracted and we don't really need to write much code to use the vocoder, because the Tortoise architecture was trained from scratch. So the autoregressive model, the CLVP model and the diffusion model were trained from scratch, while the vocoder was already an existing standalone work which was just integrated into the Tortoise architecture, because the vocoder, which specifically is the UnivNet vocoder, works so well on its own already. And we can quickly have a look at the paper of the UnivNet vocoder, and we can see that there is again a noise sequence that serves as an input and a MEL spectrogram, which will be the one that we have generated, and this is like a condition. We can also see that we have a generator and a discriminator, so this is a GAN architecture. During inference we only use the generator. We can see that some convolutional operations are used and some rectifier linear units, but since they are also vocoder that already perform better results, like the EVA-GAN, which was just published around 2 months ago, I don't want to spend too much time investigating the UnivNet architecture, but in case you're interested in vocoder overall and would like me to create a video about vocoder and maybe more recent vocoder like the BigVGAN or the EVA-GAN vocoder, please let me know in the comments and I will look into it in a future video. And while this paper promises new state-of-the-art results, I've checked it and this model is unfortunately not open source available, but what I've seen, the BigVGAN that performs better than the UnivNet that we can see here is open source available, and it's actually from NVIDIA research and was a paper at the ICLR 2023, so last year. And yeah, if you wanted to improve the Tortoise architecture, you could actually replace the UnivNet with the BigVGAN model, which likely generates even better waveform audio given the generated MEL spectrograms, but also takes more computational resources and takes longer to generate because the BigVGAN has more model parameters compared to the UnivNet. Just one thing to consider before already exchanging the UnivNet with the BigVGAN model. Alright, and then we can run this code and we can see how fast the generation of the waveform audio based on the MEL spectrograms is. So using the UnivNet is really lightning fast, and we can generate the waveform based on the MEL spectrograms in real time, which is awesome and definitely the fastest component in the Tortoise architecture. And now, after having put in so much work, we can finally listen to our speech and hopefully enjoy the great results that we have generated with the Tortoise architecture. So let's check them out. And maybe one detail, this is the sampling rate of the vocoder, so the 24 kilohertz. And yeah, let's listen to them.
Learning how AI models work and using them is fun. Learning how AI models work and using them is fun. Learning how AI models work and using them is fun. Learning how models work and using them is fun.
Yes, and I think those results are really great, and you can definitely hear the voice of Tom Hanks. In the start I wasn't sure if the folder Tom is actually related to the voice of Tom Hanks, but now you can clearly hear it. I also find it nice to hear some variety in those examples, so they all slightly differ, which is nice, so we can pick really the one that sounds best. It sounded like abbreviations are a little bit hard sometimes for the model because the last two didn't really properly pronounce AI in the way I was hoping it would be pronounced. Maybe that's something where the model can even be improved. But yeah, overall I think those generated speech results are really great and of high quality, and that's also why I appreciate the work of James Bedker so much, creating and publishing the Tortoise architecture. And that's also the end of this series. I hope you have now a way better idea of how it's possible to generate speech using the Tortoise architecture, and also on a more abstract level how you can use multiple models like large language model or an autoregressive model, a clip-like model, the CLVP model, and the diffusion decoder as an ensemble to generate speech, and also, as you saw in this video, the vocoder at the end. Yes, and that's it for the Tortoise-TTS Fully Explained series. I hope you learned a lot, you enjoyed following along the different parts. Please let me know in the comments if you like this series format and if you would like to see something similar in the future again. And yeah, I'm looking forward to see you in the next video. Bye bye.